mode. Okay, so again, thank you all for joining. This is the first of our webinars, so bear with us. We're working out a few of the kinks, but nevertheless, we are really excited that so many of you from around the world have signed up for this session today. I want to make sure that if anyone has any logistical issues, they know where to locate information on their control panel. You should all see a chat window available at the bottom of your control panel. And you can send messages to the entire group or to the organizers, and we will respond to those as soon as we can. We are recording the session today, and the presentation, both the presentation and the recording, will be available for participants after the session. And you can feel free to type your questions in the chat box as we move forward. We have carved out some opportunities during Professor Barry Lunt's talk today for you to ask questions, and he will be able to respond to those. Additionally, we have saved time at the end of the session for participants to ask questions. So even if you type a question into the chat box and it's not responded to immediately, we will be getting to it. So please feel free to send your questions along as they arise. You can send questions to the entire group, or you can send them directly to me. My name under there is AMIA webinar producer Kim Tarr. I will be fielding all of the questions and then sending them along to Professor Lunt at specific intervals and breaks in the presentation. We have also muted the audio on all participants, so chatting is going to be your way of letting us hear from you. So feel free to send us messages. At this point, I'm going to give Professor Barry Lunt the opportunity to speak and dive into his presentation. I first want to just let you know a little bit about Professor Lunt and his background. So in terms of an introduction, I'm going to share his bio with you, and then I will let Professor Lunt take the reins. Okay, Dr. Barry Lunt has taught electronics engineering technology and information technology at Brigham Young University since 1993, where he now serves as sole professor and director of the School of Technology. He's also taught electronics at Utah State University and Snow School of Technology. And Snow College. Prior to his work in academics, he worked for 7 years as a design engineer for IBM in Tucson, Arizona. He has consulted for several companies and has worked summer internships for Bell Labs, now Lucent Technologies, Larson Davis, IBM, and Micron Technologies in Utah and Idaho. His research areas are permanent digital data storage and engineering and computing education. Dr. Lunt is also the author of Electronic Physical Design and The Marvels of Modern Electronics. He's produced more than 70 peer-reviewed publications in the areas of electronic physical design, engineering education, and permanent data storage. He has 7 U.S. patents and 20 more have been applied for. So at this time, I am delighted to introduce to you Professor Barry Lunt. So Barry, I am going to turn it over to you, and you will now have the opportunity to advance the presentation.
Wonderful. My greetings to everyone that's participating in this webinar. I think it's pretty exciting to see how many people are interested in this kind of continuing education opportunity, and I'm happy to be part of it. I'm grateful to have an association with AMIA. Let's see, working on getting the controls. Okay. So you have that information about myself, and I'm happy to converse with you by way of the chat. Certainly want this to be as interactive as possible by way of questions. Another thing that I recognize is with an audience of this size, it's it's almost indelible that we have a wide range of diversity in backgrounds. So I'll do my best to make it technical enough to be of value to those who have a lot of technical background, but not using language that you can't be familiar with, that we won't cover, for those of you who do not have a strong background in that area. So, but if I cover things that I've not been clear enough on, please feel free to ask. Okay, trying to advance. There we go. The outline for this webinar, we'll talk about what analog is and what digital is. A couple of terms that you probably see a great deal in the literature today and in the media. And I think it's important to understand them. We'll compare them. We'll talk about converting from analog to digital. I hadn't planned to spend time going backwards from digital to analog. That's not a domain that I think we need to spend time on. I want to talk about digital data storage options, how we can store our data from digital data. Talk about various file formats for all digital artifacts. And we'll talk about compression, and we'll talk about some efforts to do digital data preservation, which is something that matters to all of us. Okay, first of all, analog versus digital. One of the most important things to understand about analog signals is that they are continuously variable. They have an infinite range of values. So, for example, I have an office that has a window. I'm very lucky that way. And if I don't play with my light switch, then the amount of light in my room is continuously variable. As the sun comes up, it gets brighter. As the sun goes down, it gets dimmer, and so forth. So if I were to measure the amount of light in my room, it would be continuously variable. And that's the nature of the world that we live in. The wind, the velocity of the wind is continuously variable. The velocity of your car, the temperature. Pretty much everything that we measure in the world is inherently analog. So it has a continuous variation. Examples of things that we record that are analog are vinyl records and audio tape. And that audio tape can be the old reel-to-reel tapes, the cassette tapes, any of those audio tapes prior to digital. Film, of course, is inherently analog. The color variation on each slide or each frame of a film is continuously variable. Granted, each frame is a single increment, but the range of colors and light on those are continuously variable. And the same is true of videotape like VHS or Beta, where we record the signal that varies continuously as a function of the colors and the brightness of the various pixels, as we call them, picture elements, on the screen. Some of the advantages of analog include that it gives us highly accurate reproduction. For instance, if you get some very good analog equipment, you can hear some really good sound on some recordings. The nice thing about it also is that the recording is relatively simple, and the playback equipment. It's affordable. Clearly we had record players and we had radios and we had cassette tape players and all this long before we had digital, and the quality was quite good. Granted, it's not perfect, but it was affordable and it gave us quite good resolution. The biggest disadvantage of analog has always been that it's very susceptible to noise, errors, imperfections, and degradation. And we don't notice the degradation all at once because it happens slowly. I have a good collection of vinyl records. When I first played them, they were very clean, crisp, no noise. And over the years, they've been rubbed a bit, they've collected dust. Despite whatever efforts I've made, the degradation is set in, and there is some noise, some errors and imperfections in the playback now, and so it's not as good. And then the cassette tapes are even more prone to problems because the signal amplitude degrades over time, and therefore your signal-to-noise ratio gets worse. And we all know from trying to converse with people in a noisy room that signal-to-noise ratio is critical in understanding and decoding information. Digital is different. It is discrete increments. I'm going to go over some examples of what that means. Examples of media that we have that are inherently digital are all the optical discs, which start with compact discs, followed by digital versatile discs, DVDs, and the Blu-ray discs, or BDs. When these were introduced, starting in the early 80s, they were inherently digital. So what we record on those is not continuously variable. It's these ones and zeros. Files of that type, the digital files, would include MP3, JPEG, any kind of computer data is inherently digital. I see a question that asks, why can't something be replicated digitally perfectly? I would have thought it would be the other way around. That's a fantastic question. I'm going to try to answer that when we spend a little more time on what digital is and why or how we convert it from analog to digital. Because in doing that, we have some inherent errors. In fact, one of those is right here, this quantization error. This little issue here is part of what gets into the problem. So we'll talk about that more. And then there are other ways that we can have problems due to undersampling and so forth. I see another question about laser discs. Yes, the laser discs that were introduced in the 70s were analog. So I mentioned less perfect reproduction. Those who are audiophiles still swear by analog because it does not have these types of errors, the quantization error and undersampling errors that can occur. And there are people who can hear the less than perfect digital, but myself, speaking for myself, I'll take the digital any day because it has such a dramatic reduction in this noise and errors and other imperfections and the degradation, which we'll talk about further as well. The challenge, of course, is that there's a relatively complicated recording and playback equipment needed to do that. I remember way back when I was a student studying digital audio. We didn't have any equipment that would do it because this was long before compact discs and any of the other digital media. And we did have hard drives for our computers, but they only stored 10 meg. That wasn't enough for more than a few seconds of sound. So it wasn't practical, but we knew the advantages that it would have if we could ever get to digital. And of course, now that we are there, I believe we all agree that digital has a lot of advantages because it is less susceptible to noise, errors, imperfections, and degradation. We'll talk more about why. So some of the things we want to make sure we understand are these terms: quantization error, undersampling, and then a couple more, such as sampling and resolution. Please forgive my phone ringing here in my office. I will ignore it. Okay, so here we are back to this, talking about analog. Here we have an example of a box. So this box that I have, we can set the box on the ground, and we'll call it at level 0, or we can slide this box up a ramp up to this, what we would call the loading dock level, where we can pass it off to a worker and they can load it into the warehouse. And we'll call it level 10. These are arbitrary units, maybe centimeters. But in any case, this box can be at any point along this ramp, assuming the ramp is sticky enough that it would stay there. I can slide the box up to here to a height of 4.785 or 4.786 or any height, of course, along this continuously variable ramp. So that's just one example of what analog is. And let's contrast that to digital. The digital would simply have the ground level and then the loading dock level. You'd have the 0 here, it's at level 0, and up here it's at level 1. This is what we would call 1-bit binary, and it only has 2 discrete states. So these 2 discrete states, it doesn't seem like we can do very much with just 2 states. And in general, that is very, very true. Certainly we can turn our lights on and off in our house, and that's quite useful, or in our car. So it's not completely useless, but as far as video and audio, 1 bit would be useless. So let's extend this to 2-bit audio, or 2-bit systems. Here we have 2 bits, and the little 2 down here represents the binary base. So we can have 0, 0, 0, 1, 1, 0, and 1, 1. So 4 possible combinations of these 2 bits, giving us what we call 0, 1, 2, and 3. So 4 levels. So we recognize that as stairs. So stairs are an example of digital, where we have discrete increments. We go from this level to this one, but nothing in between. You can't put a box on this because it's straight up and down. So it is not continuously variable. Moving on to a 4-bit system. We now have 4 bits here, and again, this is in binary. So we have all zeros here and all ones there, and then we increment through the 15 additional possible values to these 4 bits. going on through level 8, which is 1000, 12, and clear on up to 15. And no, we can't reach 16 with 4 bits because we have to use one of those states for 0. So that means we can only get up to 15. But it does give us 16 discrete states. Well, clearly this is a lot closer to a ramp than the 1-bit binary. If we go back, let's see, we can do that easily there. This doesn't look at all like a ramp. This looks a tiny bit like a ramp. And clearly this looks a lot more like a ramp. But this is where we get into the answer to what is quantization error. So if I have a signal that looks something like this, this is my red signal, it's analog, and this is some music that I'm listening to, for instance. But this is very much what it would look like in the time domain, meaning the x-axis down here represents time and the y-axis represents the amplitude of my signal. So this is what it looks like when I originally capture that signal. Then, of course, I try to record it in a way that is the same. When I play it back, I want to have the same thing. So there are 2 questions you have to answer when you convert from this red, which is analog, to the blue, which is my digital. First of all, how often do you need to sample? You can see here that I have in the neighborhood of 10 samples per cycle. If the cycle is from here to here, then I have somewhere around 10 samples. And you can see that if I had 20 or 30 or 50 or a million samples, I would have it much closer to the red. But I can't do that. In converting from analog to digital, I cannot sample an infinite number of times per second because that would require infinite storage. So we always have to make a compromise and sample only as often as we really have to. And it just so happens that a guy named Harry Nyquist studied this for Bell Labs way back in the early days of the telephone system. And he found that if you sample twice the highest frequency, you can recover the entire signal. When you look at this, you go, well, twice doesn't look like enough. And mathematically, it can be proven that it is enough, and also you can prove it in the lab. But I won't get into that proof here because I don't know that that's essential. But we can see that clearly the number of samples per unit time, or the sampling rate, is a key variable, and that we must sample often enough, but we cannot represent the signal in its complete fidelity. And by the way, this signal here that you see, the time from here to here is the lowest frequency in the signal. The highest frequency would be these small variations that you see. And that means I have to sample at least twice per each of these small variations. The other question is, what step size do you need? Again, you can see here that if I have a step size that's that big, it's a pretty large step size, and it's not very close to the red. Up here, my steps are smaller. It's getting a little bit closer to what the red looks like. So in this, we have probably 16 steps. Well, we can clearly see that if we were to extend that to 1,000 steps, for instance, now I would have step sizes that are so small that they look a lot more like the red. But it is not possible to make the blue, the digital, look exactly like the red unless we have both an infinite number of samples per second and a step size that is near the quantum level of physics. So it's not possible. So in all cases, what we try to do is get what I like to call close enough. So in engineering, that's the thing that we've studied for a very long time. How close is close enough so that it sounds to our human ears like natural sound, or that the picture looks like the natural world that we live in? And we've always been working hard at representing that and making it as good as we can. I hope that helps understand why digital can never be an exact representation of the analog. And then I hope to spend a little time on explaining why digital has some inherent advantages. Okay, so in the process of converting from analog to digital, we need these circuits that are called analog to digital converters, or ADCs. And there are many different types of these and many different prices that you would expect to pay. But depending upon your need, you can pretty much expect them to do what you need if you're willing to pay the price. But the needs are always dependent on the application. For instance, if I'm converting temperature, an analog signal of temperature, there just is no reason to sample temperature frequently because it doesn't change frequently. 100 samples per second is more than enough for almost all temperature variations because it cannot change at a very fast rate. Our voice is something that it does change much faster, and they found out back in the early days of the telephone system that 8,000 samples per second is enough to digitize the human voice so that somebody on the other end can recognize what you're saying. Not always who you are. We all know that our voices sound different on the phone than they do live, and part of that is because of this limited sample rate, which is a function of the limited bandwidth of the original 3 kilohertz voice signals. Audio, and the difference between voice and audio is that voice is a subset of audio. Audio, by that I mean everything that your ears can hear. Voice is just the range of frequencies necessary for us to reproduce human voice. But if we want to have audio, we want to listen to a recording of our favorite kind of music, we want to hear everything, not just some kind of poor representation of it. And that's been found to need at least 40,000 samples per second. So you can see that we're stepping up very quickly from 100 to 8,000, now to 40,000 samples per second. And that's for audio. Then we get into video. And NTSC stands for National Television Standards Committee. This is the 1960s technology, actually going clear back to the 1940s. But in any case, that's the really old stuff that we watched before we had HD TV. And in order to digitize that, you need 5.5 mega samples per second. So you can see that we're really moving up very quickly in the number of samples per second required because of the amount of information that is conveyed per unit time. Here in audio, we're conveying information 40,000 times per second. In video, millions of times per second, because every pixel, every element of our picture has to have its information, and it has to have it 24 times per second for film, or 30 times per second for television, and 60 times per second for high definition and so forth. So we just have to go faster and faster. And now moving on to HD TV, which was about in the 1990s, we move up to at least 24 megasamples per second. Now, is it possible to oversample? Certainly. You've probably heard of audio that has a 192 kilosamples per second rate, and such does give us greater fidelity. It is arguable whether that is discernible by everyone. I can't tell the difference, but some people say they can. I believe them. But this has been found to generally be sufficient, and you should know, by the way, that your compact discs have a sampling rate of 44.1 thousand samples per second. Exactly, 44.1 thousand. And it seems to work quite well. Okay, so that's the sample rate. And then the resolution, which is the inverse of the step size, resolution is equal to the step size, which is the inverse of the number of bits. So for temperature, if we have 10 bits, that generally is enough to resolve temperature down to the accuracy necessary. Now, you can get more. You can get 16 or even 24 bits, but generally that's not necessary. 10 bits will get us to 0.098% or 980 parts per million resolution. Voice, generally we have found that 8 bits resolution for voice is sufficient, and that gets us down to about 0.4% resolution. And then audio, 16 bits is what we like. That's what's on your compact discs. That gets us to 15.3 parts per million. The relationship, by the way, between percent and parts per million is just 4 more decimal places to the right. So if I take this and move it 1, 2, 3, 4, you can see that that's 980 parts per million, or 0.098%. There are different ways of saying the same thing. Let's see, I have a question about the difference between sampling and compression. That's a good question. Actually, there's no relationship between sampling and compression. Compression has everything to do with the requirements for the particular signal that we're playing with, and resolution has to do with how small of a signal do we need to resolve. I will talk about compression, and I believe that I will answer that better when we get into that compression section. I see a question here about not understanding the fractional percentages in the resolution section. And that's a question that the students always have, and I do appreciate that. Let's take an example. Let's say that we're able to resolve one part out of 100. So you have 100 steps, and you can tell which step of those 100 steps a signal is on. That's what we would call a resolution of 1 out of 100. So that would be 1%. That's what percent means, is 1 out of 100. Well, what if we had 1,000 steps, and we could resolve that one step out of 1,000? That means that we would have 1 out of 1,000, which of course would be 0.1%, a tenth of a percent. And then as we go up to 1 out of 10,000, that would be 0.01%, and so forth. Well, I'm using nice round numbers for the decimal system, like 100, 1,000, 10,000. But the binary system doesn't have nice round numbers like that. Their nice round numbers are 1,024 or 2,048 and so forth. Well, when you take those numbers, like 10 bits, that's 2 to the 10th is 1,024. So if I take 1,024 and I take 1 over 1,024, that's where I get 0.098%. Remembering that 1 over 1,000 would be 0.1%. So 1 over 1,024, just a little bit less than 0.1%, 0.098%. I believe that addresses that, and I hope it does. And we'll move on to the next slide. Oh, no, I didn't talk about color video. Excuse me. So for NTSC and HDTV, we have found that 8 bits of color seems to be sufficient. So granted, NTSC is not digital, but in digitizing it to make it look like the analog version of NTSC, 8 bits of color was sufficient. And for high definition television, we've also found that that's the case. And remembering that there are 3 colors, red, green, and blue. Interestingly, if you can vary the intensity of red, green, and blue subpixels together, it will look like continuous range of colors. So if I turn on red, green, and blue in equal intensity, it looks like white. If I turn them all off, it looks like black. If I turn on only the red one and leave the green and blue off, then of course it looks like red, and so forth through green and blue. And then combinations of those, varying the intensity of each individually, gives us a pretty wide range of palettes, and we can control the screen to represent basically all the colors. Not all that the eye can perceive, but a wide range of them. So if we have 8 bits per color, that's 0.39% per color. And if we have 3 colors, red, green, and blue, then we wind up using 24 bits. So if you hear somebody talking about 24-bit color, that's what they're talking about. 8 bits per color, or 256 possible colors for either red and the green and the blue, for a grand total of 2 to the 24th, which is a very large number. I see a question about, what about black and white? How many bits necessary for black and white? Well, that's a good question. It turns out that the resolution for black and white is about 4.5 megasamples per second, and we only need 1 color, and 8 bits of resolution for that 1 color is sufficient. So we can drop this down to 4.5 megasamples per second, and instead of 24 bits, we can get away with only 8 bits, because we just have the black and white color variation. Okay, well, we must confess here that digital, the ones and zeros of conversion, like I showed before, such as 0000 or 1111, that's not what we actually record on a digital recording media, such as a compact disc, because it's just much more complex than that. So, for instance, we have to record also these things called error correction coding bits. We always add those, and the range of those can be anywhere from 10 to 25% overhead. I need to say a little bit about what those bits are. It's metadata, and I hope that we're all familiar with what metadata is. It's data about the data. So if I take a whole series of ones and zeros and run it through a special coding circuit, that special coding circuit will give me a specific code. And if I store that code on the recording medium, then when I play it back, and some of my bits are read back incorrectly, which, by the way, they always are, some are always wrong, I can take that special code and identify which ones were in error and actually fix them. Because obviously if I know exactly which bit is in error, I just flip it. If I read it back as a 0 and it's wrong, then it's got to be a 1. It's either 1 or 0, so that's easy. Identifying which bits are in error is the challenge. Flipping them is easy. So I always add this error correction coding because reading back digital data never gives you back the exact same 1s and 0s that you recorded. I hope that doesn't make you too nervous. It is the case for all digital recording. We also have what we call formatting, and framing bits. And what we mean by that, of course, is how do we identify a song on a CD? Well, clearly we have to have metadata, music about the song, about the artist that recorded the song, and so forth. So that's part of the formatting information that separates the 1s and 0s into separate tracks, as we like to call them, on the CD. There are also framing bits, because every so often I have to know exactly where I am in the playback process, so I can make sure that I'm in the right place. Because clearly, if I were to get out of sync, the sound wouldn't sound at all like what was originally recorded. So we have to record framing bits, and these are special sequences of bits that are not allowed in the normal sequence, and that gives me the ability to know where I am in the bit stream. There are also what we call clock recovery bits that are always added. And what do we mean by that? Well, back to this example of music. If we're recording 40,000 samples per second, then I know that every 40,000 times per second, I must produce a sample. Well, how do I have a clock on the end of the readback? The readback end doesn't have a clock, and yet it needs to be exactly the same as the clock on which it was recorded. How do you do that? Well, it's really quite tricky and quite amazing, but the fact is that the solution means you always have to add a few extra bits in order to recover the clock. And then the next thing we do is we take this final data stream, which includes these ECC bits, the formatting and framing bits, and the clock recovery bits, and we just stir them all up, but in a very fixed way. We interleave them, we mix them together in a very specific way to avoid burst errors. And I debated whether to spend time talking about burst errors. I think that's beyond the scope of this webinar. Suffice it to say that most errors are bursty, meaning they occur in small pieces of time and they destroy a whole lot of adjacent bits. Well, if I have a whole lot of adjacent bits destroyed, then I can't play back what was destroyed. But if I interleave it and then de-interleave it, I can. And it's powerful and it's wonderful, it works very, very well. And then a final confusion factor that we add is that the ones and zeros that we record on a recording medium are actually not ones for the highs and zeros for the lows, but rather the ones represent a transition between 1 and 0. It doesn't matter whether the transition is from a 0 to a 1 or a 1 to a 0, it represents a transition. And if there's a 0, it represents the lack of a transition. So if it was a 1 before, it stays a 1. If it was a 0, it stays a 0. And that sounds dreadfully confusing, and perhaps it is. I apologize if I've just made things messier, but the fact is it's much, much easier to detect transitions than it is to detect levels. So most digital recordings are done with the 1s and 0s representing transitions rather than levels. So I see a question here, is the ECC run each time by the reader? The answer is yes. The ECC is always used to check and make sure that the data is read back correctly. And where there are errors, they're fixed. As I mentioned, there are always errors in the readback. And the other question that this reader or this participant asked is, the correction happens each time the data is read. Yes, that is correct. Because every time you read back the 1s and 0s, the reader has no idea what was originally stored there. If it knew it, it wouldn't bother to go read it. So it's trying to figure out what's out there, and in order to do that, it must always run these ECC bits through the decoder and fix the data as it needs to be fixed. Okay, so what does it mean for this, for the readback process? It means that everything that we did up here before we actually put the 1s and 0s onto the recording medium, whether it's tape or discs or whatever it is, a flash drive or a hard drive, we have to do it in reverse. Okay, so that means that the ECC is operating and fixing the errors as we go. The clock, we have to derive the clock from the data, and we have to make sure that that clock varies exactly the same as the data stream, because the data stream actually varies in speed. And you go, well, why would the bit stream change its speed? The answer is the media that we play this back on is often rotating. Disks are rotating, hard drives are rotating, and their rotational velocity is not constant. It changes slightly, and we have to accommodate those variations. Likewise, if we're reading it back from our flash drive or our tape, there's going to be variations in the data rates of those as well. And then lastly, of course, we have to de-interleave this mess that we made up here, but thankfully, because we do it in a fixed way, we know exactly how to de-interleave that. Trying to advance the slide here. Have I lost control? It doesn't say that I've lost control. I have lost control. Okay, there we are advanced. So now let's talk about the storage media options that are available to us. There are actually only 4 classes. There are optical disks, hard disk drives, digital magnetic tape, and flash memory. I am not aware of any other type of storage media today for digital data. Now, again, I'm not talking about analog. I'm talking about digital. And we've already talked about optical disks and the fact that we have compact disks, which have a capacity of about 750 megabytes, digital versatile disks, or DVDs, which have a capacity of about 4.7 gigabytes, and Blu-ray disks, which have a capacity of about 25 gigabytes. One of the most significant things that has been done by the optical disc industry is that they have made all of these versions of disks backwards compatible. Now, that hasn't been easy to do. A huge amount of engineering work has been necessary, but it's been very obvious from the start that anybody that had a DVD player wanted also to read CDs, and likewise with BDs. Anybody who buys that expects to be able to play DVDs and CDs on them, and that backwards compatibility has been maintained. This is unique. If you look at all these other 3 options here, that hasn't been maintained, and so that's something we'll talk about later. And I should mention webinar 1-8 will spend a great deal more time talking about the specific storage media, their characteristics, their advantages and disadvantages. So if it seems like I'm skimming over this today, it is true, and it will be covered in much more detail in webinar 1-8. Also under optical disks, we have 4 subcategories, one of which is probably not familiar to you. But we have the stamped ones, and by stamped I mean the ones that you buy in the store pre-recorded. They have your favorite music on them or your favorite movie in NTSC resolution or HD resolution with a BD. So those are pre-recorded. They're actually not stamped but injection molded, but they're called stamped. Then recordable ones, that's the -R or +R media that you can buy that actually have a die, and that the media information 1s and 0s are recorded in this die. So those are recordable. Then we have rewritable, which simply means, of course, that they're erasable. They're recordable and erasable. And again, more about that in webinar 1-8. And then one that you've probably not heard of, which is magneto-optical, and I'm not going to get into that one today, and only a tiny bit in webinar 1-8. Then we also have 2 versions of some of these. We have standard density Blu-ray, for instance, and high density Blu-ray. And the standard density, as I mentioned, is 25 gigabytes. The high density is 33 gigabytes for Blu-ray. The DVD high density did not catch on. It wasn't introduced originally, and the CD did not have one. Okay, so leaving optical disks, let's talk about hard disk drives. The internet lives on hard disk drives. Anything that is on what we call the cloud means it's on hard disk drives somewhere. These are not removable media. You can't take the disks out. Don't try it. These can also be external, which means that they're not inside your computer but can be plugged into your computer externally. The densities of these are really quite amazing, continuing to rise at about 14 to 15% per year. And I've seen those rise from 10 megabytes now up to the multiple terabytes range, and the price has just remained incredibly affordable. And these are usually in what we call a redundant array of inexpensive drives, or sometimes disks. I see both in the literature. We call it RAID, which just means that we have more than one disk, that's what the redundant part is, and that the same data is recorded on both disks. That's what the redundant part is about. And that's why we call it an array, because if we have multiple ones, and we keep the same information on two, so that if one dies, the other one has the same information that can be recovered from that. And of course, there could be more than two in the RAID array. I should mention that we'll spend more time on RAID in webinar 1-8. And if you say, well, RAID 0 doesn't have redundancy, that's true, and that's why it's called RAID 0. It's not really RAID, although it's called that. So most storage on hard disk drives does use RAID because hard disk drives are notorious for having catastrophic failures. Probably a lot of you have experienced this in having stored a lot of your information on a hard drive, which then crashed, and you lost it all, and that's not an unfamiliar story, which is why we use RAID to take care of that problem. Digital magnetic tape is another option, and half-inch tape is by far the most common of that physical format today. There certainly are other physical formats, but as I mentioned, half-inch tape is most common. The linear tape open standard, which comes in a cartridge, is the format that's the most common for industry today, and that's generally not used by consumers, but mostly by the cloud, by people who have large data centers and they want to back up their hard drives onto something more long-lasting and less high maintenance. And digital tape has filled that option very, very well over the years. The really big advantage of tape is that it has a very high capacity. Digital tape can store an entire hard drive. None of these others can generally do that. And the cost per cartridge is quite low, so the cost per bit is very affordable, and that's what makes it advantageous. And then finally we have, of course, flash memory, which is in two basic formats: the thumb drives, which are also known as flash drives or jump drives or dingets, or I've heard a number of other things, especially when they don't work. But it's the same technology as solid-state drives. Solid-state drives are just this flash memory made to look like a hard drive. The computer sees it and thinks that it's a hard drive, treats it like a hard drive, but it's not a hard drive, it's a solid-state drive, and it's stored as flash memory. And again, we'll talk more about what does solid-state mean and how does this technology actually work in webinar 1-8. Somebody's asking a question. Can you address the advantages and disadvantages of video stored on hard disk and solid-state disks from an access, retrieval, speed, and quality standpoint? Wow, that's a great question. Because of error correction coding, and because that in general is robust and able to withstand a great deal of problems with the data, the quality, in other words, the accuracy of the bits that are read back on hard disk drives and solid-state drives are at parity. They are essentially the same. It's very, very rare that you get what we call an uncorrectable error, which means an error that the error correction coding cannot fix. So both of those are on a par. As far as access, hard drives suffer from the fact that they are not fully randomly accessible. If my data is on the opposite side of the disk from where my head is, I have to wait for the disk to spin around under the head. I also have to move the head over to the right track to access it, and that takes a range of milliseconds, anywhere from 3 to 10 milliseconds, depending on the speed of the hard drive and a couple of other factors. That's not a long time, but as far as video, it can cause pauses in the readback process. Solid-state drives don't suffer from that. Their readback time, the access time, the time from when you ask for the data to when you get it, is in the range of 100 nanoseconds, or on a hard drive it's in the range of 10 milliseconds. So you can see a 7 orders of magnitude, or 10 million times difference in the access time between solid-state drives and hard disk drives. But once the data starts coming, the two are at parity. They're both able to supply the data at the same rate and at the same reliability or quality. So as I mentioned, these are the 4 media options that we have. There's lots of different subcategories within them, but those are the 4 More on that in webinar 1-8. One thing to recognize, though, is that every time we store a 1 or a 0 on storage media, what we actually do is we store it as a change to the material. It's just like if you paint a wall, you store the color of the wall in the paint. And you can't store 1 or a 0 without changing the media that you actually store it in. So in recordable optical discs, for instance, we have a dye, and we actually change the reflectivity of that dye to make it a 1 or a 0. For magnetic materials, it's pretty straightforward. We put a magnetic field there, and we magnetically orient the particles on that disc or on the tape to have north and south poles. And we're able to read that back as 1s and 0s. And then the last example is the solid state or flash memory. We have a small capacitor built out of a floating gate, and again, more in the webinar 1-8. And it's the amount of charge, the amount of electrons that we store on that capacitor that we interpret as a 1 or a 0. Now, as I mentioned before, all of these have errors in the readback process. It is not possible to read back digital data with 100% reliability. So generally those errors are fixed by the error correction coding because it's quite robust. What that does is it hides from us as the consumer how unreliable the data is. So for instance, if I'm getting 1 error per million bits, I can fix that easily. The error correction coding can fix that very, very easily. But if I suddenly get 1,000 errors per million bits, that's getting up to the region where the error correction coding is going to have a problem. But it probably can fix it. So let's just say that it does. So now you're reading 1,000 bits in error per megabit, but you're doing it okay. You don't see any difference at all between that 1,000 bits in error and the 1 bit in error because they're all fixed by the ECC. So that's why you never know how close you are to becoming unreadable. For instance, if it's 10,000 bits in error per megabit that causes problems, and that generally would for most recording media, you don't know how close you are to that until you try to read a file back and your computer says, file unreadable. And that's not a happy experience. So that information is not available to the consumer. It is available. I have certainly worked with it a great deal in my research, but it's rarely given nor understood by consumers because they don't care about it. What they care is their data. They stored a file, they want to read the file back, and all they care is reading the file and moving on, and that's as it should be. We don't want them to have to worry about that kind of mess. I see a question, but who is to blame for the errors? Well, what a great question. The carrier, the recording device, the reading device, the codecs, or the digital in general? And the answer is all culprits are guilty to some degree. The carrier is probably the primary culprit, the recording device to a lesser degree, the reading device is probably as guilty as the carrier. The codecs, generally no. They have very little blame. They are generally quite good if they're designed correctly. They can be under-designed, and that would be a problem. Or the digital in general. Digital in general, I guess I would have to exonerate the digital. It's not inherently to blame for the errors. The other things are. So we can exonerate the digital. The other ones are all guilty to some degree. Okay, back to where we were. All storage formats change over time, and that's one of the huge issues that anybody in the digital storage realm knows and is frustrated by. We all are familiar with floppy drives, floppy disk drives. We're familiar with magnetic tape formats that are no longer relevant. We're familiar with other formats that have changed over time and have become irrelevant. So this is an issue, and I'm going to talk more about that again in webinar 1-8. So the best solutions to long-term storage are to refresh, which means you take your data on an old tape and rewrite it to the same tape. And yes, that's legal to do. It's just fine, but don't make a mistake because you can lose the old data before the new data is rewritten. Or migrate, which means take the old data from an old storage medium and put it on a new one. So that's migrating. Or choose a medium which is the most stable over time. And of the four that we've discussed, by far the most stable is optical disks. Compact disks having been introduced over 35 years ago, still usable, still readable, still the same format. and there's billions of them out there. So that this appears to be quite stable, and of course the same with DVDs and Blu-rays seem to be quite stable for time. So I seem to have lost control of the cursor, which means I've lost control of the keyboard. That means I've lost control of advancing the slides. Any help you can get, that would be great. Good. Okay. The way that data is organized is that the smallest unit is a bit, and I think we've all heard that term. And by the way, that's a contraction of binary digit. A lot of people didn't know that, but that's what it means, is a binary digit. And 8 bits together we call a byte, spelled with the Y. And then when we organize these together in larger groups, we call them kilobytes, megabytes, gigabytes, terabytes, petabytes, exabytes, zettabytes, and yottabytes. And no, I didn't make these up. These are standard terms in the industry. This term I've seen a great deal in the literature. Once in a while I'll see this one. This one I've only seen on the standards page. Yottabytes is such a large number that don't have a lot out there that's needing to talk about that. Let's see. A couple of questions here. Internet Archive asks 15 petabytes and counting. Here we are in the Internet Archive, 15 petabytes. That's huge. That's a great deal of storage. 2 to the 50th, or 10 to the 15th, if that's more comfortable to you. This is 10 to the 12th, 10 to the 15th, 10 to the 18th, 10 to the 21st, and 10 to the 24th power. That's just huge, 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 huge numbers. Question, another one here says, is optical more stable than magnetic media? Stability is my area of research. My whole area has been permanent digital data storage, and I have to tell you that of the 4 options rather, yes, optical discs are more stable. And especially as you get into the LTO6 and future LTO standards, they are having real problems with longevity, multiple years. So more about that again in webinar 1.8. I'm not sure why. Sometimes I'm not able to advance the slides. I've lost control again. I see I don't have the cursor. There we go. Okay, so some characteristics about file formats. These are 7 characteristics that, based on the literature that I've read, we all agree these are desirable for long-term storage of digital files. 1, that the format not change with time. That seems pretty straightforward. Number 2, that it accommodates all types of data. Clearly, we want to be able to store pictures, moving pictures, sound, temperature, velocity, Word files, spreadsheets, whatever it is. We don't care what the data is. We want to be able to store it on whatever it is we keep it on. Number 3, is it flexible enough to accommodate future needs? And of course, who of us has a crystal ball and can predict the future? But the beautiful thing is that the people that design the future storage can make things backward compatible. And where that focus has existed, you can pretty well guarantee that you will have some future-proof dependability because they've cared about it. The example being half-inch tape people haven't cared about it, and optical disc people have. Again, more about that in webinar 1A. Number 4, that it does not compromise the quality or integrity of the original data. That's definitely a given. But we'll see when we get to compression that that's not always the case. There are some types of compression that do compromise the quality and integrity. Number 5, that it can be easily deciphered, meaning that it can be read back easily, that it doesn't take an act of Congress and bills and so forth to take care of that. Number 6, that it work on all computing platforms. We don't want to care about whether it's on Windows or an Apple OS or Linux or whatever there may be in the future. We want all of that to work. And finally, that it regularly accommodates and organizes metadata. Data without metadata tends to be so much less valuable. And so we want a file format that just makes metadata an integral part of it, allowing us to keep that metadata with it. Next slide. I don't have control of the cursor. There we go. So one thing to recognize is that the file format and all the characteristics that we talked about on the previous slide are a function of the originating program. What do I mean by that? Well, you have a spreadsheet, and you store the spreadsheet on something. Well, what format is that spreadsheet stored in? That's a function of the spreadsheet program that you use, like Excel. They're the ones that decide what the format will be, and if it's stored on a half-inch tape, it's in a different format than if it's stored on a hard disk and so forth. And I'm talking about the micro format. Formats differ by a great deal, and unfortunately they are dependent upon the type. There are text formats, there are formats for still pictures, formats for moving pictures, formats for music, formats for other things like we mentioned, spreadsheets, databases, Word files, relational data descriptions. And then these data types are generally not interchangeable. In other words, if I have a text file and I want to convert it to music, that is a very difficult thing to do. We could certainly write software that would do that. But generally, because that's not done, it's not easy to interchange those. Next slide. This is a summary of some information that I pulled from the archival website, Gov archival website, that you'll see some links to on the next slide. But there are several things that we want for file formats, and here's some examples for still images. I'm not trying to be exhaustive here, these are just representative. So we have GIF files, JPEG files, JPEG 2000, PNG, portable network graphic files, and TIFF files. And this is what they say is their stability over time. They're all good. None of them are excellent. None of them are outstanding. But the good news is none of them are terrible. Some of them have a high flexibility. One of them does not. Fairly low flexibility. Future-proof. This one's not very future-proof. We have three that appear to be very future-proof and one that's good. Image integrity. And that has, again, primarily to do with compression and the type of compression that is used, which we'll get into in the next few slides. Decipherability, what do we mean by that? How easily can this information be deciphered? And the answer is it's low on all of them. No human, can look at any of these digital file formats and read it back. So you've got to have a computer to read it back. And finally, the cross-platform compatibility, which we talked about in the desirable characteristics. We see some variations here. And this, again, this is not exhaustive, but it's just representative of a few still image formats. Next slide. So a few more things about formats for audio and moving images, which are the ones that this audience primarily cares about. The best file format is one that's widely adopted. The example here is Latin. Why is Latin still taught today in schools around the world when no country and no culture uses that as their first language? It's because there are millions of documents that were written in Latin, and they still exist today because the Roman world was the Latin world, and the Roman world was huge, so it was very widely adopted. Another counterexample is Linear A, a language spoken on a small island in the Mediterranean Ocean. We still don't know how to read it. It was not widely adopted. So if you want a standard to last a long, long time, get one that's widely adopted. Second, one that does not compromise sound or image quality, which means it has, the compression is lossless compression. More about that on a subsequent slide. We want it to work on multiple platforms. That's pretty straightforward. And finally, one that allows multiple playback resolutions, qualities, and sizes. Because we never know what somebody's going to use to play it back on. They might be watching it on their phone, they might be watching it on their huge HD TV, and so we have to accommodate all these sizes and all these resolutions and the various qualities. So here's those links that I promised you, digitalpreservation.gov, about audio formats, and a summary of about video formats. Really good information there that I felt was a little bit beyond the scope of this webinar, but I highly recommend it to you for further reading. Well, the answer is, which of these formats are we going to choose? The answer to that question is, unfortunately, no single format meets all those qualifications. But we do have some tools that help us judge among them. Okay, I see a question here. Let's see if I didn't miss one. Is the low decipherability the reason why you have to also archive the device that plays something, a problem celluloid film did not have? And that's a great question. The answer is yes. Yeah, film, if you look at it with your naked eye, you can read it. But without the device that recorded it, for playing it back, you have nothing. You have a bunch of colors or not even that. Yes, it's undecipherable. I have a question about, could I put the lists to the guides into the chat box so we could copy them elsewhere? I'm not sure what the lists to the guides, the web links. Oh, yeah, because you don't have access to those, do you? Let me see if I can do that. Let's see. I don't seem to have control over the slides. Well, that's rather frustrating. I can't move ahead or back. Well, I'm going to have to ask if we can put those links in something later. I'm sure that Kim will help me through that. So moving on slides, let's talk about compression. There are two basic types of compression. I need to back up one slide. We have lossless compression and lossy compression. Lossless means that the original data can be completely recovered. And so that's its big advantage. The disadvantage is you can't compress it very much, typically only about 50%. And we'll talk about the respective file types. And there's the lossy kind, which means that you can compress it more, but the disadvantage is you are left with degraded information. You cannot recover everything that was originally there. And we'll talk about the respective file types there. Let's move to the next slide. So lossless compression, it looks for, oh, we skipped ahead too, I think, didn't we? Yeah. Lossless compression looks for patterns in the data. Like if you see a whole bunch of ones in a row, that's a pattern. So then you produce a special code that represents that pattern. And then you record those codes and what we call a lookup table that says pattern 11369, oh, excuse me, that's not digital, 1116, 11110011, so forth, represents such an else. So we wind up having codes that represent patterns, longer patterns, and we can compress those that way. So we record the codes, and then we record the lookup table, and therefore that's a type of compression. The types of lossless compression are unique to the kinds of files that we're working with, specifically whether they're video, audio, and still frame pictures. And this stuff is essential for data files and spreadsheets and Word documents, programs, financial information. You've got to have lossless compression. You cannot avoid loss of any of the bits. So these kinds of files have to be stored with lossless compression. As I mentioned, you can only usually get about 50% compression. Repeated efforts of compressing will get you nowhere. Examples of lossless compression files are zip, PNG, GIF, WAV, and JPEG 2000. Lossy compression looks for pieces of lesser importance. For instance, there's always something in the data that you can get by without. And so we look for that in either the audio, the video, or a still picture, and we wind up compromising the integrity of the data by throwing that information away. So we use audio and video perception theory, how we as humans perceive this information, and therefore we can record at various levels of loss that are acceptable in certain cases. So I mentioned before, the original file cannot be fully reproduced from the compressed file, and there are three types of lossy compression: spatial, temporal, and mathematical. And we'll spend a tiny bit of time on each of those. Examples of these types of compression are MP3, JPEG, MPEG, and almost all your video streams that are streamed through the internet. Spatial compression looks for repeating patterns. It uses the difference between one line and the next. For instance, if I look at this line right across here, there's a whole lot of zeros, or white here, and then some dark, and then some white. There's a lot of patterns through there. So I look for those patterns, and I simply reduce those patterns between one line and the next, because this line and the next line are very, very similar. I take that periodic reference, and then I install periodic reference bytes to start at a new reference point. Because if I only use deltas in between, then I wind up losing integrity. The classic example is a fax transmission, which I'm going to show you in a minute. So this is an example of spatial compression. Here's my original picture, and this one is at full resolution. I don't remember what it was, but the point of it is, this is what it looks like when we compress it spatially. You can look at this and see a significant amount of degradation between this and this signal, although in a lot of cases this is acceptable, which is why we do it. This is an example of the fax. Fax machines store information at 200 pels, or print elements per inch, and 200 lines per inch, which would give us a resolution of 1700 by 2200 for a single 8.5 by 11 page. That's 3.74 megabits per page. And on a phone line at 4,800 bits per second, that gives us 13 minutes per page. Well, if it took you 13 minutes to transmit every page of fax, you wouldn't use fax. Not that most of us use it today anyway. But in any case, that's impractical. And I had a student who said, Professor Lunt, this is really interesting. Can I play around with this a bit? And I said, for sure you can. So he took this idea and created a fax page that couldn't be compressed spatially. So he created this page here, and you can see there are no patterns in this at all. And this is a blown up portion of that page, and you can see there are no regular patterns. So when he tried to transmit this back in 2003 in one of our labs here, it took 12 minutes, and then the fax just crashed because it couldn't compress it enough to be transmitted. Now to temporal compression. This is only useful for video, which means moving images, because it uses the difference, the deltas, between one frame and the next. So clearly, if I'm watching two people talking, the difference between one frame and the next is very little. Their mouth may move, their eyes may blink, but the rest of it's pretty much the same. So I can save, excuse my phone again, I can save a lot of bits by simply using the deltas. I can represent the difference between one frame and the next. And again, we use periodic reference frames in order to start a new reference point as necessary. Classic examples are YouTube videos. I have a couple here that I have links to that, for the interest of time, I'm not going to show, but I encourage you to watch them. These are what I consider to be examples of intolerable compression. Compression so bad that it's just it's so unpleasant to watch that I wouldn't continue to watch it. The artifacts abound. By an artifact, we mean that you can see imperfections, things that didn't come out right when we compressed it. There's blockiness, there's a small color palette, there's blurring. All of those are artifacts of overcompression. And the quality on the internet varies all over the place. You can find YouTube videos that are wonderful, high resolution, and others that are just terrible. And I have these two examples. By the way, I don't know anything about the people behind those videos. I apologize if I'm offending somebody. I didn't mean to. Okay, this is the last slide. I wanted to say something about digital preservation efforts because there is a great deal of interest in preserving digital. Digital has a lot of weaknesses, one of which is long-term preservation. Analog, like pictures and prints and celluloid film and so forth, just has a much, much longer lifetime. And digital has some inherent problems there. Well, there's the OIS community, Open Archival Information System. It's an organization of people and systems, and they have an international standards committee that created this standard, and a consultative committee for space data systems that created another standard. A lot of interest in keeping this digital data, which of course has been around since satellite days. We want to keep that for decades to come. Then there's this LOCKSS. Lots of copies keeps stuff safe. And while it sounds like a good idea, and it is, it's more than an idea. It is an official program started at Stanford University. The basic idea being if you have the same information at multiple locations, you have it safer than if you keep it all in one place. We have the Northeast Document Conservation Center, which is both a paper and has both paper and digital initiatives for preserving documents, and their focus is on funding grants. And then the Digital Preservation Education, which this website that I've linked, that I've mentioned before, is concerned about. It's talking about the best practices and guidelines in digital preservation. Okay, so the next slide basically is my references and the credits, and then the upcoming webinars. So let's go back to the last question, which I did not get to. Last question says, what suffers more in lossy compression of moving images? Color, sharpness, transition between images, and so forth? Well, that's a great question. And I'd have to say again, all culprits are guilty as charged. They all suffer. The examples that I linked to on YouTube are probably good examples of that. You can see that there's problems with color, there's problems with sharpness, and there's problems with transitions between images. All of them have suffered from the compression. And that's characteristic of lossy compression, where we throw away these difficult to store or difficult to keep pieces. The high resolution pieces, the high sharpness are difficult. Okay, so Kim says she's going to send along some questions. Waiting to see what those questions might be. Okay, we would like to have access to the actual webinar after today. I hope that AMIA makes that possible. I think that's a great idea. Oh, good. Kim says that the PDFs will be uploaded after the session. I hope you find them useful.
Great, Barry. I'm actually going to jump him as well. I want to make sure that folks know that we have about 12 minutes remaining in the session. If you want to just go ahead and send your questions in via chat, and Barry can tackle those. I see many questions coming in, so I'll let Barry take a look. We will be sending out the PDF of Barry's entire presentation, and that will be available both via email and also uploaded to the Materials tab in GoToTraining. So Barry, I'll transition back to you.
Thank you, Kim. First question I see here is, will there be more discussion of framing bits and clock recovery? I don't plan to spend more time on that in webinar 1-8, so let's just say a little bit more about it here. It would be very helpful if I knew the exact nature of the question. I can get into this as deep as we want to go, but I don't know that that's what we want to do. Suffice it to say that all digital recording does have framing bits because of our need to keep track of where we are in the data stream. We can't just look at a bunch of ones and zeros and know where we are unless we have that. And the way that we create a framing bit is we simply have a specific pattern of ones and zeros that are not allowed in the data, but are allowed as control bits or framing bits. And so when we see that specific series of ones and zeros, we know that we've encountered a framing bit. Clock bits are extra bits that are inserted into the data that allow the clock to detect when an edge has occurred. So now we know the difference between period 1 and period 2. For instance, if each period is 10 nanoseconds wide, then every 10 nanoseconds I need to have a new bit period. And by keeping the bits in proper sequence, I can use what we call a phase lock loop circuit that actually locks onto these bits coming through and knows approximately what the right clock frequency would be and is able to recover it by following the variations in the bits as they come in from our rotational device or from a satellite, for instance. That also gives us variation in frequency. Another question says, I hope that's enough, if not, ask again. Another question says, sorry to come back to the same topic, but it really intrigues me. What are the ongoing efforts to reduce errors? Wow. Let's just say that thousands, probably tens of thousands of people are working on that. But it goes directly counter to the problem of storing data in greater densities. If I want to put 750 megabytes on a 5 1/4 inch optical disc, that's fairly easy compared to putting 25 gigabytes on the same optical disc, because my bits have to be smaller. Well, if the bits are smaller, that means the signal that I read back is also smaller, which means my signal-to-noise ratio is worse, which means I have a much more difficult time reading the data back without errors as I put more data in less space. In other words, as my hard drives get higher in density, as I put more bits in less space, I lose integrity of the data. So what usually happens, at least always as far as I'm aware, is we simply increase the amount of error correction coding. So instead of only 10% overhead, we may bump it to 15% overhead, or 18%, or 20% overhead. And that additional overhead, while it does reduce the amount of place that we can actually put data, because now we're dedicating 4/5 of the room to the data and 1/5 of the room to the error correction coding data, the advantage in density that gives me, which may be 2 times or even 5 times greater, is by far overwhelmed. So error correction coding has immense power. A 1% increase in error correction coding will give us a 10 times or even 20 or 30 times increase in our density. And so that's generally most of the work goes is into error correction coding. A lot of work been going on in that area. And so basically the bottom line is, are we reducing errors? No, we're actually making them worse. Are we increasing our ability to fix the errors? Yes. So far, so good. So somebody says yes, and more on clock recovery would be awesome. So more on clock recovery. Well, that's a good question. As we read back to data, let's say that we know that our data rate is 1 megabit per second. That means that the nominal data rate coming is 1 megabit per second. So I set a clock on the receive end or on the read back end of my, let's say it's an optical disc that I'm reading. I set the clock to 1 megahertz, and that means normally it's going to expect data every 1 microsecond, so a million times a second. But because my disk spins at slightly varying rotational velocities, that 1 megabit per second is going to change slightly. So I take this circuit called a phase lock loop, and you'll find plenty of good information on the details on that guy on the internet. Just Google phase locked loop, or PLL for short. It will tell you how it works, but basically it follows the variations in the clock. So as the data comes in, you get ones and zeros. You're guaranteed that because of the way that we force the data to be through these special clock bits. And as every time you get a 1 is a transition. The transition tells you when the clock needs to tick. And so when that transition occurs, the clock goes tick. And if the next time the transition occurs sooner, the clock ticks sooner. If it occurs later, the clock ticks later. So then the clock follows the variations in the input data, and we use that same clock to decipher the ones and zeros. It's a fascinating technology, phase lock loops. They've been around for 50, maybe 60 years, long time. Very useful, very, very heavily used in industry. See, there's a question as well about the general lifetime of storage mediums. That's a fantastic question that I intend to answer in detail in webinar 1-8. Didn't feel that it was quite as relevant to this one. Could I elaborate on future-proof when it comes to image formats? Oh dear. Future-proof seems to be mostly a function of what has the standards group done to keep it backwards compatible. The example that I gave was the optical disc industry. They have cared a great deal about backwards compatibility for all 3 of these major formats, the CDs, DVDs, and BDs. And so, given that track history in the past, it's pretty sure that the future will be compatible as well. And so I think that's probably the best answer to that question. Let's see if I see any more questions here. General lifetime. Yeah, definitely more on the general lifetime of the storage mediums and why in webinar 1-8. It's future-proof. Looks like we still have 5 more minutes for questions. I think I've addressed all the ones that I see. If not, shoot them there again. I dodged that one about the lifetime because we're doing that in webinar 1-8. Saw a question here. Optical discs do not store very much. Could capacity be an important consideration for future proofing? Yes, there's certainly it's certainly the case that we always want to store more data, but there are solutions. There is the high-density Blu-ray disc, which is 33 gigabytes. There is a triple layer high-density Blu-ray disc for 100 gigabytes, and there is a dual-sided 100 triple-layer Blu-ray disc that can be used today. And these are, again, if you buy a player that can record and play triple-layer dual-sided Blu-ray discs, they will also play and record CDs, DVDs, and Blu-rays. The backwards compatibility has just been amazing in the optical disc community. So 200 gigabytes on an optical disc is good. Granted, it's not terabytes. Will that change in the future? It's being worked on. It is a very difficult thing to do, but I suspect that that's going to continue, but it's going to have to be backwards compatible. Could capacity be an important consideration for future proofing? Oh, that's the one I just addressed. In webinar 1.8, will you also discuss costs associated with various storage options? Yes. There are some tables that will summarize a comparison of those, as well as their longevity, their practicality, and some of how it works. Let's see. Where can folks send in comments about what they liked or didn't like? I'm sure that Kim knows the answer to that one. At least I hope so. And I'm very happy to receive feedback as well. I want to make sure that this is as useful as possible. Any other questions? Looks like Kim has answered that question. Thank you, Kim.
Great. So much, Dr. Barry Lunt, for this wonderful presentation. I wanted to give folks an opportunity to send along questions. We have a couple minutes left. If not able to get to your question today in today's session, then we can undoubtedly get back to you. So Barry had included his contact information at the beginning of this session, and we can make sure that again. I can advance back to the beginning. Just a moment. Barry, do you have anything else to add?
No, I think the questions have been fantastic, and the interaction has been great. And Kim, your job as the moderator, thank you. You did great.
Oh, thank you. Here again is the contact information. There seems to be an issue that it's not in the slideshow mode, but nevertheless, here we go. You should have Barry's contact information on the screen now. And on behalf of the AMIA Continuing Education Task Force, I want to thank everyone for joining us today. This was our first and we would love to hear your feedback. So